This video is going to talk about the likelihood ratio test. So in the previous video we talked about deviance, and we talked about how the difference between the null and the residual deviance tests the null hypothesis that all the betas in the model are equal to 0, and I noted that this was just like the f-test that we were doing with linear regression. This test turns out to be a special case of a very important hypothesis testing tool for us, which is the likelihood ratio test. So this likelihood ratio test is it's the analog to all of the f-tests that we were doing earlier. So the general linear hypothesis test is what I think I called it earlier. So suppose that I have a model that, let's call it the full model, and this full model has p plus q predictors in it. Suppose also that we have a reduced model that has only the first p of these predictors in them. So the difference between the full and the reduced model is that in the reduced model, the last q predictors, so that's going to be these, right? So we have beta 1 through beta p, and then the last q of these betas are all constrained to be 0, so they're not in the model. Now, how do we compare the full versus the reduced model? The answer is we want to compute the deviances for both models and compute the difference. So if D1 is the deviance of our full model, and D2 is the deviance of this reduced model, it turns out we can test whether it's plausible that all these betas for those last q predictors are in fact 0 by simply looking at the difference in these deviances. So this is a chi-square distribution with q degrees of freedom. Now let's go back to the problem we did. Let's think about what we had here. The null model was this reduced model, so we could think about having p equal to 0 predictors and q equaling 1 predictor. All right. Now the 1 predictor is the slope. So if we go down to the reduced model, so p equals 0 predictors, all we have is the intercept. This is that would be like the deviance of the reduced model is that null deviance. This is the deviance of the full model. What is the difference in the degrees of freedom? Well, 1 degree of freedom has been deleted, and that's why this difference has a chi-square distribution with 1 degree of freedom. Let's try another problem now. We're going to return to that pizza restaurant problem. Now, in the pizza restaurant problem, recall that we had 3 predictors: food, atmosphere, and service. We were predicting the likelihood that someone was going to be returning to the restaurant. Now let's have this reduced model. So you can think of p equaling 2 predictors. So food and service, q equaling 1, which is atmosphere. So then the question is, if we constrain beta 2 to be 0, that's my null hypothesis, do I explain significantly less variation when doing that? All right, so how do we do this test? We have to compute the deviances of the 2 models, subtract them, and then that difference will have a chi-square distribution with, in this case, 1 degree of freedom, since I'm only constraining 1 parameter to be 0. So let's find the first deviance. Remember, deviance is 2 times the likelihood, log likelihood. So the deviance for the full model was back on page 123. Let's go just confirm that. So here was that pizza restaurant problem. The residual deviance, here we go, is 2026.2. And so that's where that number is coming from. How are we going to get the deviance for the reduced model? Well, I'm going to have to fit that. Let's go do that. So here is regressing purchase intent on food and service. Now this problem has some missing values in it, and if we don't account for those missing values correctly, it's going to not give us the correct answer. So I only want cases where atmosphere is not missing, because the full model didn't allow any missing values for atmosphere. So anyway, if I fit this model, I get a deviance of 2027. So we can think about the amount of additional explaining that's done by adding atmosphere to the model is the difference between 2027.9 and this 2026. So that difference is under 2. It's like 1.77. Now that difference will have a chi-square distribution with 1 degree of freedom. So that's why I'm writing that here. And I get a p-value of about 18%. Now, estimating the full model and then estimating the reduced model is it's a bit of work. R will automate that for us with the drop one command. So if we go back to the original fit, so that's the fit from the pizza restaurant slide on page 123 that we just looked at. If we do a drop one on that with a chi-square test, this is what we get. All right, so actually it does likelihood ratio tests for everything, for all the parameters in the model, but notice we have this, in the atmosphere row, we have all the numbers that we've just derived. So the full model has this deviance, 2026. Reduced model, I guess this is rounding it. So if we round this to the nearest, 1 decimal place, that rounds up to 2028. The difference between 2026 and 2028 is this likelihood ratio. LRT stands for likelihood ratio test. So this is the LRT statistic. We go look that up with a chi-square distribution. How many degrees of freedom does it have? Well, 1. And notice we get exactly what we got below. Well, doing a likelihood ratio test for one predictor is not that interesting. Let's look at one where we really need to do this because all right, well, yeah, anyway. So let's go back to the fitness club data set. Remember with the fitness club data set, we had the dependent variable is whether or not a customer would default on their membership at the fitness club. And I think I had 3 predictors in that model. So we have the log of down payment, the log of use, and then the most interesting variable for this example is the payment type. So payment type is categorical. It takes 4 values. So the 4 values are book, which is the base category in this model, statement, checking EFT, and credit EFT. Now, we could ask ourselves, do we really need payment type in this model? All right, so do we need these 3 parameters, or is it plausible that all 3 of these parameters are really equal to 0? So our full model is everything you see here. It's going to have 6 total parameters. The reduced model is going to be where we constrain these 3 dummies to all have 0 slopes. All right, well, how do we do the likelihood ratio test? Let's do it the easy way. So we'll just do drop 1 on this fitted model, and the line down here gives us the answer. So if I constrain, I guess I can't highlight just that 3, but that 3 means payment type is associated with 3 dummies. If I constrain all of these dummies to be 0, so that's my reduced model, notice the deviance goes up to 14,324. Now, the deviance of the full model is 11,477. If I subtract these 2 from each other, I get the likelihood ratio test statistic. Now, this has a chi-square distribution with 3 degrees of freedom. And if we go look that up, it's very highly significant. So if you want to confirm this kind of the hard way, if you will, here I estimate the reduced model. So there's the reduced model. The difference in the deviances, sure enough, is 2846.6, which is what I got up there. I used the chi-square cumulative distribution to find a p-value of 0. That 0 is just 2.2 times 10 to the minus 16th rounded. So the ideas that we've been talking about, so AIC and the likelihood ratio test, are also used in doing stepwise and backward selection, so model selection. So recall that there are these automated procedures for building a model. Let's see how that works with the problems we've been talking about. So if I'm going to make a smaller version of the defaulting customer data set so that this runs quickly. So this command, sample, picks 500 cases, so the 500 is specified here, at random from 1 through the number of rows. So in essence, I've drawn a sample of 500 cases to make this a little bit more interesting. All right, now let's go back and we're going to try this model. So the log down payment, we're going to throw payment type in. Let's do age and gender just to give us some other stuff in the model. Now if I do a backward selection just by typing step fit, let's trace through what R does. So with backward selection, we're going to begin with everything and try to start dropping variables. So it says that if I get rid of gender, my AIC is actually going to get better. So it goes from 277.5 down to 275. We want small AIC. Looks like we can get rid of gender. We don't want to get rid of these other variables because AIC actually goes up. So 277 to 319. So since backward selection is a greedy heuristic, it's going to do the best thing at this point in time. It gets rid of gender. Next step, let's see if we can get rid of anything else. Well, if we get rid of age, looks like AIC improves further. So it goes from 275.5 to 274 point something. So age goes next. What do we consider next? Well, we've got two things left. And the point is, if I get rid of either of these variables, my AIC goes way up, so the algorithm stops. Now, one thing to note is step is smart enough to know that this payment type is really a set of 3 dummies. So in essence, it's doing a likelihood ratio type thing, where it's subtracting the deviance for the reduced model without those 3 from the deviance of the full model. All right, so that's one example. Let's look at another one. In this case, we're going to do kind of a forward selection on this. So remember, to do forward selection, we start out with the intercept only, and then we add. Here are the variables that should be considered. I like to call these the candidate variables. So the first thing in is payment type. AIC goes from 340 down to 300, so that's a good move. The next thing in is it brings in down payment. Another good move, it goes down to 274, and here it says I can't add anything else, and so the algorithm would stop.